Electrical storms are one of nature's most spectacular and unpredictable phenomena. Despite our technology, we remain powerless to control this awesome force. Nevertheless, the conditions that cause lightning are at the very heart of a groundbreaking experiment at NASA Lewis Research Center in Cleveland. The Solar Array Module Plasma Interaction Experiment, or SAMPIE, is an essential step toward the development of future high-voltage power systems for space exploration. Dr. Dale Ferguson is principal investigator of the SAMPIE project. He and his team are nearing the most critical phase of the experiment, flight testing in low Earth orbit.
Before Earth-based technologies are used for space applications, they must be thoroughly tested to ensure that they will perform as needed in the space environment. Flight testing is crucial to the engineering process.
Historically, electric power generation in space has relied on photovoltaic solar arrays. Photovoltaic cells, commonly made of silicon, are semiconductors that convert visible light into direct electrical current. The cells are covered with a transparent housing that allows light to easily penetrate them. Excess current is stored in batteries. Photovoltaic power is routinely used in such low-voltage items as calculators. The amount of current created by photovoltaic cells is a direct function of surface area. The greater the surface, the greater the power. Cells are connected in small units called coupons, and coupons are strung together in larger sheets known as solar array modules.
Photovoltaics has proven to be a reliable source of electricity for the 28-volt power systems inherited from the aviation industry. However, future space exploration will require higher voltages, as much as 160 volts DC.
On Earth, when you want to increase the power of a photovoltaic array, you increase the number of cells. And as the number of cells goes up, so does the power. In space, adding more cells increases the voltage that the system will operate at. And a high voltage in space can be a problem for a spacecraft.
When we think of the space environment, we immediately think of zero gravity. However, what poses the gravest problem to designers of a high-voltage power system is space plasma. Plasma is created when a gas is subjected to high temperatures or bombardment by ultraviolet rays from the sun. The electrons are literally stripped away from their normal orbits around the nucleus. When this happens, the gas, which is normally an excellent insulator, becomes a fairly good conductor of electricity. This chart depicts the density of the plasma relative to the altitude above the Earth. The density decreases as we increase in altitude. For low voltages, plasma does not present much of a problem. But at high voltages, in low Earth orbit, it's a stumbling block.
When the electric potential between 2 points is great enough, the gas between them ionizes, creating a path of low resistance for electricity. And when that happens, arcing takes place, and undesirable and destructive current is unleashed. It's lightning, with all of its hazards and unpredictability, only on a smaller scale.
Arcing can destroy or degrade most materials it contacts, from the delicate solar arrays to such durable materials as anodized aluminum, which is used as the primary structural material for satellites and other space payloads. Arcing can also cause current disruptions that could hamper in-space operations of every type. Among the important questions the SAMPIE flight test will help answer are:
at what voltage does arcing occur?
At what rate does arcing occur?
At what intensity?
And specifically, what effect will arcing have on all the various materials and geometries currently designated, not only for the solar arrays, but for the whole space station?
Will other materials need to be found?
How can we protect them?
And ultimately, what steps can be taken to eliminate or minimize arcing?
The SAMPIE payload consists of an electronics enclosure with an experiment plate fixed to the top surface. It will be mounted directly to the top of a Hitchhiker M carrier. The instruments and electronics that run the experiment and record data are located inside the enclosure. The experiment plate will expose more than a dozen different materials, geometries, and technologies to conditions identical to those the space station will encounter.
Extensive ground testing is always conducted first and is critical to research. But certain conditions are simply impossible to simulate on the ground, such as pressure, plasma flow, and electron temperature. For example, results from previous flight tests of silicon solar cells differed radically from the ground tests of those cells.
The SAMPIE experiment plate will flight test leading-edge technologies, but more familiar materials are also represented.
All U.S. spacecraft that have flown to date have used silicon solar cells. They therefore will provide a baseline for us to allow us to compare our data with data that has been taken in the past. Even though other technologies are more efficient, silicon is still the cheapest and is still the most commonly used. We have to take a look at what happens to silicon then.
Also to be tested is a coupon of advanced photovoltaic solar array, or APSA cells. These cells hold great promise because they are much thinner and lighter than silicon. SAMPIE will also test the impact of arcing on several state-of-the-art alloys being considered for use on the space station. When the SAMPIE experiment completes its set of flight tests, the on-orbit data collected will be brought back and analyzed by scientists and engineers at the Lewis Research Center. This flight data will provide the foundation for developing future high-voltage space power systems for NASA into the 21st century and beyond.